Hello students, welcome back. Let us begin section 2, Kramers Rule. We have three theorems here, one really important and the other not very much. This is the important one. Let A be a square matrix of dimension n and let B be a column vector of dimension n. Then we have this equivalence. Determinant of A is non-zero if and only if the matrix equation Ax equals to B has a unique solution. By the way, have you seen the right-hand side Ax equals to B before? This is, as a matter of fact, this matrix equation as a matter of fact, is a system of linear equations. And we have done this kind of thing before. Ax equals to B has a unique solution if and only if, a special case, Ax equals to 0 has a unique solution. In this case, what do you mean by unique solution? This is homogeneous system. So x equals to 0 is always a solution. A times 0 is equal to 0. So what do you mean by unique solution? That means it has only trivial solution, nothing else. Non-unique solution means it has other solution, non-trivial solution. So these two are equivalent, or the way we used to write in module 3 was like this, has only the trivial solution. And that is equivalent to this non-homogeneous system having a unique solution. Of course, here the focus is the determinant. So we're not going to pay too much attention to this part, the homogeneity. However, some ideas related to this homogeneity actually do come here, so do not forget completely about this. Now, if you want to review a little bit, you can always go back to module 3, maybe module 4, maybe both. Okay, let's begin. We're going to prove like this. When determinant is non-zero, we have to prove the right-hand side. And then when determinant is equal to 0, then we have to prove that this solution is not unique. Okay, so if this is true, then that's true. Yes. Now converse. If this is not true, then this is also not true. That's what we're going to do. Forward direction, that's a bit more straightforward and that's easier. So let's assume determinant is non-zero. Then A is invertible, as you saw over here. Determinant is non-zero if and only if inverse matrix exists. So what can we do? You can multiply the inverse matrix A inverse to both left-hand side and right-hand side and simplify. A inverse times A will cancel each other out because that's the identity. And what do you have? X is uniquely determined by A inverse times B. So we have a unique solution. This algebraic proof here is really easy, isn't it? So if you get the right setup, determinant is non-zero, and then try to prove this way, it's not difficult if you remember all the ideas. Next, let's suppose determinant is 0. Then, by theorem 1.1 here, the column vectors are linearly dependent. As you see over here, determinant of 0 if and only if all the column vectors are linearly dependent. You can use rows, but columns are a little bit more convenient here. So how do you do? Linearly dependent. So you can write a linear combination equal to 0 vector, yet not all coefficient is 0. What do you mean by linearly independent? That means if you have a linear combination equal to 0, then everything has to be equal to 0, and that's being negated here. Not all of them is equal to 0. In other words, this n tuple is not a zero vector. This capital Y, this column vector, is not a zero vector. Okay, how does it help? Like this. From ax plus b, ax equals to b, sorry about that, let's replace x with x plus ky. Okay, here's the matrix equation, ax equals to b. Here, solution x is replaced by x plus ky. Now what happens? Break off the parentheses and we have ax, which is equal to b, no problem there. And then how about this part? K times ay. And what is ay? What's ay? What can you get from here? Ay is equal to 0 vector. So b plus 0, so we have b. Conclusion. When you have x is a solution of this, ax equals to b, then x plus ky is also a solution. A times this is equal to b as well. So we have two different solutions. Actually, infinitely many more because this k is arbitrary real number. Okay, that completes the proof. Is everybody comfortable with everything? In case there are some students who are not really getting ay is equal to 0, let me explain it here. This linear combination with all those column vectors tells me ay is equal to 0. Why? Here we go. y1a1 plus y2a2 plus all the way over to yn an is equal to 0 means ay is equal to 0. Why is that? a1 is this column vector. a2 is this column vector. And so on. This an is this column vector. So this expression on the left-hand side is equivalent to this expression in the left-hand side. So this and that are the same. Here a1, a2, a3, and so on are just abbreviations of these column vectors. No problem there. And we are using this color coding and it'll help you. Next, how about this right-hand side? Ay is equal to 0. It's like this. A is the square matrix given by putting all those column vectors together and times y is equal to 0. So this right-hand side is equivalent to that. Now the question is this left-hand side and right-hand side equivalent to each other? You can check. How about the first component here? The first, a11 times y1, a12 times y2, dot dot dot, a1n times yn, add them all up and we have 0. Well, first row times this column dot product is equal to 0. Yes, they're equivalent. How about the next line? Second row times this column dot product is equal to 0. Does it work that way? a21 times y1 plus a22 times y2 plus and so on, a2n times yn, adding them all up equal to 0. Yes, indeed, they're the same. Same for all the rows. That is the reason why this linear independence, or linear dependence, excuse me, that thing is telling me ay is equal to 0. And we use that one. That's equal to 0. So we have this another solution. By the way, this part here, setting ay is equal to 0, basically we are setting up the homogeneous equation and then adding up the solutions of homogeneous equation. So basically that's the same thing we had been doing in way back in module 3 and 4. Same idea. Okay, that completes the proof of theorem 2.1. Proof was okay, but also the conclusion itself. Non-zero determinant means the system of linear equation is well posed, we have unique solution. Next, Kramers rule. Okay, here is a computational formula for the system of linear equations. And this one, as a matter of fact, is actually a system because A1, A2, A3, all these are column vectors, and B is also a column vector. So this is a vector equation, n-dimensional vector equation. So this is basically a system of n linear equations. And we have n unknowns with n equations. Yes, we can solve it, theoretically at least. And is it really well posed? That depends heavily upon determinant is 0 or not. If the determinant is non-zero, then yes, we have unique solution. Not only that, the unique solution looks like this. Each aj can be calculated as denominator is determinant of A, and the numerator is determinant of A, where jth column is replaced by column vector B for xj. And then, of course, we have to repeat it from x1, x2, x3, all the way over to xn. So there are n solutions like this. How many determinant computation do I have to do? We need determinant computation for denominator, and then we have n numerators to calculate. J equals 1, 2, 3, all the way over to n. So this is, as a matter of fact, enormous computation. So it's not really practical. I already said this was computational formula, but I kind of regret it because we don't usually use it as a computational formula unless we have really small dimension, like 2-dimension, 3-dimension, kind of like that. For higher order, this method is not really useful. Gaussian elimination is actually far more useful if you use computer algebra system. By the way, okay. In case there are some students who really didn't understand what you mean by these determinants notation, it's just this column vector in the right hand side over here goes in place of jth column vector. This should be A. Okay, let's prove it. How do you prove? Proof is relatively okay, considering that this formula is not really useful. The proof is quite elegant, as a matter of fact. Okay, let's begin with the numerator. And we have B in place of the jth column. But B is equal to this linear combination. So we just put this linear combination in place of B, the jth column. And then we can use multilinearity to break everything up. Take x1 out, and then a1. Next, takes x2 out and a2. Take x3 out and then a3. Here, take xj out, and then we have aj. Repeat, repeat. In the end, we take xn out, and then we have an. Now, what are these determinants? We have an and another an, so that's 0. And then before that, an minus 1 and another an minus 1, that's 0. Here, a1 and a1, that's 0. a2 and a2. In short, everything disappears except for the jth column, where there is no duplicate. So here we go. Jth column, we have j, so that's determinant of a. And dividing by that determinant of a, we have xj. Okay, that's the first Kramers rule. And then there's another Kramers rule, and this is Kramers rule for inverse matrix formula. Goes like this. Determinant of A, like before, and then over here we have determinant of the deleted matrix, Aij, and then -1 to the I plus j power, and then transpose. That's the determinant. Excuse me, that is the that is the inverse matrix formula. Okay, how do we prove it? Let's begin from A times B is equal to I. And have you seen this before? In theorem 1.1, in the proof of theorem 1.1, we have this A times B is equal to I, yes, and that was associated to this system, B11, A1 plus and so on, for arbitrary ith row here, then it will be B1I, A1, B2I, A2, and so on. And that's over here. Instead of writing all those, I simply wrote ith row. And then we saw that this is generating that in the proof of theorem 1.1. Okay. By the way, do I have further explanation here? Okay, all right. Okay. So if I rewrite everything I did as in theorem 1.1, we get something like this. First linear combination equals to 0. Oh, excuse me. That's not it. Sorry about that. That's not a repetition of what I did in theorem 1.1. This is the short version of theorem 1.1. And this one is a longer version of this because this EI is a standard basis vector. We have all 0, 0, 0, 0 except for 1 in the ith row, and everything else is again 0. So that's what we have in the right hand side. And then we have A1, which is A11, A21, A31, and so on, AY1, AN1 like this, and AJ, this column, A1J, A2J, A3J, and so on and so forth. So we have this system of linear equations, and that's actually this. And if you use theorem 2.2 Kramers Rule, then you can solve for this BJI like this. Replace EI in place of the jth column. This is ith, not jth, okay? Ith, EI goes to the jth column. And then denominator, we just have AJ, so that's determinant of A, no problem there. Now, how about the numerator here? Let's calculate this determinant, but it is best to expand it with respect to the jth column, because you see at jth column, we have a bunch of zeros, except for one I in ith row. So here we go, all zeros, all those are 0 except 1 in the ith row. So we have j plus I there. And then removing ith row, and then jth row already, because this came from jth column. So we have deleted matrix Aij, everything else gone. So we have -1 to the I plus j power times determinant of Aij, the deleted matrix, over determinant of A. That's Bji. And what is Bij? We have to take the transpose. There goes the proof. The proof of this Kramers rule, the second version for inverse matrix formula, is more confusing than difficult because there are so many indices. And as for practicality, not very much either, to tell the truth. If you want to calculate the inverse matrix, typically you use Gaussian elimination. Computers calculate much faster in Gaussian elimination too. So as a computational formula, this is not that useful either. but we went through it, and that's where we're going to stop.